if you're building or, deploying autonomous coding systems right now, you are almost certainly managing execution environments for those agents.
Oh, absolutely. It's unavoidable.
Right. And if you're like most engineers in the field, you're trying to provide your models with system-level guardrails.
Yeah, which in the current architectural paradigm usually means initializing your repository with an agents.md or a Cloudivade.md context file.
Exactly. It's become this ubiquitous industry standard. We see it explicitly recommended by major agentic frameworks.
Right, from open hands to SWE agent.
Yeah, they pitch it as the best way to align model outputs with repository-specific constraints. We essentially treat it as a required optimization baseline.
We do. We just assume it helps.
But what if standardizing your repository interactions through these static context files actually, well, degrades your system's overall performance?
It's a critical question, especially for those of us optimizing deployment pipelines, because we are fundamentally dealing with an assumption of additive utility.
Additive utility, right, meaning more data equals better results.
It's exactly. The prevailing logic in machine learning architecture dictates that injecting global repository context, things like style guides, structural overviews, tooling directives into the agent's working memory at step 0 is going to optimize its navigation.
It just feels logically sound. You assume that feeding the model more highly relevant context yields higher precision in the output.
Right, but we need to test that assumption.
Okay, let's unpack this. The objective for this deep dive is to critically examine a rigorous empirical study from researchers at ETH Zurich and LogicStar.ai.
It is a fantastic paper.
It really is. It's titled Evaluating Agents.md, Are Repository-Level Context Files Helpful for Coding Agents?
And they didn't hold back on the models they tested either.
No, they didn't. The authors take state-of-the-art models. We're talking Anthropic's Sonnet 4.5, OpenAI's GPT 5.2 and GPT 5.1, along with Alibaba's Qwen 3 30B coder.
A really solid lineup.
Yeah, and they run this massive, highly controlled evaluation to see if these standard context files actually improve autonomous task completion.
And honestly, the empirical data fundamentally challenges the current developer recommendations.
Spoiler alert for everyone listening. The assumption of additive utility are mathematically false in most practical, real-world deployment scenarios.
It really is. But to really understand why the data challenges those recommendations, we have to look closely at the structural validity of the evaluation itself.
Right, benchmark setup.
Yeah, you can't just throw models at a problem, right?
Yeah.
You need the right benchmark. Before this paper, the community standard for repository-level evaluation was SWE-bench.
Specifically, the SWE-bench Lite variant.
Exactly. But SWE-bench has this inherent evaluation gap when it comes to measuring the true utility of context files.
And this is something I think a lot of benchmark designers struggle with. SWE-bench Lite is built on highly popular, incredibly mature Python repositories.
We're talking about projects like Django, Matplotlib, or scikit-learn.
Right. Now, these repositories existed long before the formalization of the Agents.md standard back in August 2025.
Yeah, they don't natively contain developer-written context files.
But more importantly for ML practitioners listening to this, these code bases represent the absolute center of the parametric training distribution for any frontier model on the market today.
That is the core issue right there.
Yeah.
I mean, think about the pre-training data mixture for a model like GPT 5.2.
It's seen it a million times.
Exactly. It has seen the Django code base thousands upon thousands of times across GitHub scrapes, Stack Overflow discussions, official documentation.
Its weights are deeply optimized to understand Django's architecture already.
Right. So if you inject a high-level overview of Django's directory structure into its context window at runtime, it's fundamentally redundant.
You aren't measuring the agent's ability to ingest and utilize novel dynamic context.
No, you're merely measuring its ability to process duplicated tokens that it already has stored in its parametric memory.
Which skews the whole evaluation.
Exactly. To address this structural insufficiency and actually isolate the variable, the researchers had to engineer an entirely novel dataset.
Which they called AGENT.bench. And I'm glad they did, because AGENT.bench is specifically designed to isolate that context variable without relying on those heavily memorized code bases.
It's a huge step forward for evaluation.
Can you break down exactly how they sourced the data for this benchmark?
Absolutely. So the authors sourced 138 real-world Python tasks from 12 distinct, highly niche repositories.
Okay.
Crucially, Every single one of these 12 repositories natively includes a developer-written context file in its root directory right out of the box.
So it fundamentally shifts the evaluation away from those legacy code bases.
Exactly. It moves it toward active, modern repositories where context files are actually being utilized and updated by the maintainers in real time.
But building a reliable benchmark out of niche repositories is notoriously difficult. How did they handle the testing environment?
The methodology they used to construct AGENT.md is highly rigorous. They extracted tasks directly from pull requests that introduced deterministic, testable behaviors.
So both bug fixes and feature additions.
Yep, both. But here's the catch. Because these are niche repositories, they often lacked the strict, comprehensive testing protocols you would expect to find in a massive open source project like Django.
Ah, right.
So the researchers had to implement a specialized LLM pipeline to generate comprehensive regression and unit tests for these specific pull requests.
And what kind of coverage did they get?
They achieved an impressive average code coverage of 75% doing this.
Okay, wait, I have to stop and push back on that methodology for a second. This sounds like a potential red flag.
How so?
If the researchers are evaluating LLM coding agents using regression tests that were also generated by an LLM pipeline, how are they preventing data contamination?
Ah, the golden patch issue.
Exactly. For those listening who are deep in benchmark design, you know the fear of the golden patch, the original developer's actual cunning that fixed the bug.
Right.
If the test generation pipeline inadvertently leaks the specifics of that golden patch into the task description or the test itself, the agent might just copy it.
And then the entire benchmark becomes an artifact of data leakage.
Right. How do they ensure the tests don't overspecify the implementation details?
That is a vital security concern for benchmark integrity, and it's exactly the right question to ask. The authors anticipated this exact contamination vector.
Oh, they did. Good.
Yeah, they implemented a highly stringent multi-agent filtering process to prevent it. They didn't just have one model write the whole thing.
How was it separated?
A distinct, isolated agent was utilized solely to generate standardized task descriptions. This agent was strictly instructed through system prompts to separate the observed behavior of the bug from the technical specification of the fix.
So they essentially built an informational firewall between the problem definition and the original developer's patch.
Exactly. It ensures the target solution does not bleed into the task prompt. But they went a step further, actually.
What else did they do?
After the generation pipeline, rigorous manual review was applied to any test that appeared even slightly overspecified.
Oh, wow. Manual review is labor-intensive?
It is, but they needed to guarantee that the tests only validated the deterministic behavior requested in the issue ticket.
Like checking if a specific function returns the correct integer.
Right, and not the specific syntax or architectural choices of the original golden patch.
That validation step is absolutely crucial for trusting the results.
Definitely.
So moving forward, we have a structurally robust testing environment with AGENT.bench, and we also have the established SWE-bench Lite for legacy comparison.
Which gives us the foundation to measure the actual delta in performance when context files are introduced.
Right. The researchers evaluated the agents across 3 distinct settings. Let's define those really quickly for the listener.
Sure.
First is the none setting, meaning absolutely no context file was provided to the agent. Second is the LLM setting, where the context file was auto-generated using the agent framework's built-in initialization command.
And third is the human setting, which utilized the actual developer-provided context file native to the repository.
Okay, so what did the empirical data actually reveal across those 3 baselines?
Well, what's fascinating here is the highly counterintuitive nature of the performance metrics. Let's look at the LLM setting first.
Those are the auto-generated context files that most major frameworks currently advise engineers to initialize, right?
Exactly. Across the board, they actually reduced task success rates.
Wait, reduced?
Yeah. On SWE-bench Lite, the resolution rate dropped by 0.5% compared to the baseline.
Wow.
And on AGENT.bench, dealing with those niche repositories where context should theoretically matter more, the resolution rate fell by a full 2%.
It's a strict, measurable degradation in system capability.
It really is.
But the drop in resolution rate isn't even the most punishing part of the data. It's the operational overhead.
Oh, yeah. The compute costs.
Right. If you're managing compute budgets, this part is painful.
Yeah.
The inclusion of those LLM-generated context files increased inference costs by roughly 20 to 23% across the evaluated models.
It's a massive jump.
It is. Furthermore, it drove up the average step count by nearly 4 full execution steps per task. You are mathematically paying significantly more in compute resources for a lower probability of task resolution.
And when we examine the human setting, the context files carefully curated by actual repository maintainers, the data shifts slightly, but the underlying problem remains.
How so?
Well, developer-provided files performed marginally better than the none baseline, yielding a 4% average improvement in task resolution.
Okay, so human context is better than no context, barely.
Barely. However, this marginal gain still incurred a massive operational penalty. Step counts inflated by an average of 3.34 steps, and inference costs still drove up by up to 19%.
Here's where it gets really interesting, especially from a systems architecture perspective.
Yeah.
We're looking at a glaring behavioral discrepancy in the agents. If step counts and inference costs are rising by over 20%, the models are clearly dedicating substantial computational resources to processing and acting upon the context file.
They aren't just ignoring the extra text in the prompt.
Exactly. So why does the resolution rate actively drop, especially with the auto-generated files? What is happening inside the execution loop?
That's the big question.
Are the agents hallucinating invalid tool commands because of the extra context? Or are they getting trapped in repetitive execution loops trying to satisfy conflicting constraints?
To answer that question regarding computational overhead, we have to pivot away from the macro success metrics and dive granularly into the agent telemetry.
The actual execution traces.
Right. The authors conducted a highly detailed trace analysis of specific tool calls. They wanted to understand the behavioral shifts induced by these files at the action level.
And what did they find?
The telemetry proves exactly what you hypothesized.
Right.
The agents aren't ignoring the context. In fact, they're exhibiting what we can describe as hypercompliance.
Hypercompliance. So the models are aggressively executing whatever directives they find in the text, regardless of the localized task requirements.
Precisely. We can see this in the attention mechanisms prioritization. When specific tools like NuFi for dependency management or PyTest for testing are explicitly mentioned in the context file, their usage frequency spikes exponentially in the execution trace.
Do we have hard numbers on that?
We do. To give you a hard number, UV utilization jumps to 1.6 times per instance when it's included in the context file.
Compared to what?
Compared to less than 0.01 times when it's omitted.
That is a massive delta.
Right. The attention heads heavily weight those tool tokens. So the agent reads the directive to use a specific tool, and it immediately biases its execution path to deploy that tool.
Whether it is strictly necessary for the localized bug fix or not.
Exactly.
The telemetry data shows this induces what we can categorize as a hyper-exploratory state. Across all the tested models, when a context file is present, the agents execute more grep operations, they read more files across the directory.
They execute more write operations.
Yeah, and they run significantly more tests. They are dramatically expanding their search and verification space before they even write a single line of code.
And we can actually quantify the cognitive load of this hyper-exploratory state by looking at the reasoning token data from the adaptive reasoning models.
Because models like OpenAI's GPT 5.2 and GPT 5.1 mini automatically scale their reasoning tokens based on perceived task complexity.
Right, so we can use their token consumption as a direct proxy for computational friction.
What did the token data show?
When LLM-generated context files were present, GPT 5.2 consumed 22% more reasoning tokens on SWE-bench Lite.
And the mini model?
GPT 5.1 mini consumed 14% more.
So the models are mathematically working harder to process the environment constraints before they even begin to solve the specific pull request issue.
Yes.
They are burning through their reasoning budgets trying to achieve global alignment rather than focusing on local problem solving. This creates severe thread contention for the model's focus within its working memory.
That's spot on. If we connect this to the bigger picture of system design, these context files act as an instruction tax.
An instruction tax. I like that phrasing.
Yeah, because in any autonomous agent architecture, you are operating with finite resources. You have a limited context window, a bounded reasoning budget, and critically, a strict maximum step limit for the execution loop.
Right.
When you inject a repository-level context file at step 0, the agent attempts to strictly satisfy those overarching repository rules.
Right. It runs the prescribed linters across the whole repo, it navigates the suggested directory trees, and it attempts to utilize the specified dependency managers.
Exactly. This expands its execution space to a degree that actively depletes its context window and its step limit.
So if your loop is capped at, say, 30 steps.
Exactly. By the time the agent finishes verifying the global environment and finally isolates the actual bug it was tasked to fix, it's at step 28.
It's approaching the termination threshold of the harness.
So it fails out. The global context is actively making the specific, localized task harder to resolve because of that thread contention.
That perfectly frames the mechanism behind the degradation. The instruction tax is bankrupting the agent's step limit.
Yep.
But this brings us to a crucial architectural question that the paper tackles. If LLM-generated files are actively detrimental, we have to isolate the root cause. Is the issue simply a lack of model capability during the generation phase?
Right, the capability hypothesis.
Yeah. For instance, if you use a lightweight quantized model to generate the initial AGENTS.md file, maybe it just writes a poor, confusing file. Or, conversely, is the fundamental concept of a static global repository overview conceptually flawed from the ground up?
To isolate this exact mechanism, the researchers conducted a series of highly targeted ablation studies.
Okay, let's go through them.
The first ablation directly addressed the model capability hypothesis. They compared context files generated by the specific framework's default underlying model, which might be smaller or highly optimized for speed, against context files generated by a uniformly stronger frontier model, specifically GPT 5.2.
So if the problem was simply poor generation quality from smaller models, deploying GPT 5.2 to write the context should have mitigated the performance degradation.
But the empirical data shows that deploying a stronger model to write the context file does not solve the problem.
Not at all.
No. Even when GPT 5.2 generated the context files for all agents, the performance on AGENT.bench still fell by 3%.
A more capable model writing the static rules didn't prevent the instruction tax from degrading task resolution.
Exactly. And this points directly to a flaw in the static overview concept itself, regardless of how elegantly the rules are written.
Which is fascinating.
We can observe this fundamental flaw clearly in what we might call the overview fallacy. Current industry guidelines highly recommend including a structural overview of the repository, like a directory tree map, in the context file.
Which seems entirely logical to human engineers.
Right, and the generation prompts natively follow this. 100% of the context files generated by Anthropic's Sonnet 4.5 included directory overviews.
But what did the trace analysis show?
The trace analysis revealed something striking. These overviews provided absolutely zero navigational advantage to the agents.
Zero advantage. For anyone designing agent prompts right now, that is a stunning metric. You would logically assume a directory map would reduce search time.
It would. But when the researchers measured the number of steps required before the agent interacted with a file relevant to the specific pull request,
Yeah.
the metric remained statistically unchanged whether the overview was present or not.
That is wild. Why is that?
The reason goes back to how models process information versus how humans do. A developer looks at a directory tree to build a mental spatial map. An LM agent doesn't navigate spatially. It uses semantic search. It executes find or grep commands to locate the specific function definitions it needs to patch.
So the high-level map doesn't replace the need for localized semantic search.
Not at all. It just adds tokens to the prompt, taking up space in the attention heads without providing a functional shortcut.
Which leads us to the redundancy ablation. This is perhaps the most revealing experiment in the entire paper.
Oh, definitely.
The authors hypothesized that LLM-generated context files are highly redundant with existing repository documentation. To test this hypothesis, they created an informational vacuum.
They literally went into the repositories and systematically deleted all other documentation.
They stripped out the Raychev files, they deleted the entire docs folders, and they removed all inline example code.
And in that highly artificial stripped-down vacuum, the LLM-generated context files suddenly became useful.
Really? By how much?
Performance actually improved by 2.7%. When you systematically blind the agent to the native documentation of the repository, the auto-generated summary finally provides a measurable signal that the attention mechanism can leverage positively.
So what does this all mean for you, the engineer listening to this right now? It means that in any standard, well-documented repository, an LLM-generated context file is essentially redundant noise.
Completely.
It merely duplicates parameterized knowledge or summarizes existing documentation that the agent could have discovered organically through grep if it actually needed it.
Yeah, it adds context window noise, it biases the attention mechanism incorrectly, and it triggers the instruction tags.
All without providing any uniquely actionable signal.
And that explains why the human-written context files provided that marginal 4% improvement we discussed earlier.
Because they actually contained novel information.
Exactly. They worked because they occasionally contained uniquely actionable signals, idiosyncratic, hyperspecific tooling requirements, or bizarre build commands that fall entirely outside the model's parametric training distribution.
Right, a human maintainer knows the undocumented quirks of their legacy build pipeline. An auto-generation script just summarizes the directory names.
Precisely. We need to distill these findings into core technical takeaways for your immediate workflow. If you are configuring a framework like OpenHands, SWE-agent, or Claude Code today, the empirical data strongly advises against using the built-in initialization commands.
Like running init to generate LLM context files for your repositories.
Right. You are mathematically likely to increase your inference cost by 20% while actively reducing your autonomous resolution rate. It is a lose-lose scenario.
Furthermore, if you are actively maintaining human-written context files, they should be strictly minimized. You must discard broad architectural overviews, directory maps, and general coding guidelines.
The agent already possesses general coding guidelines in its pre-trained weights, and it will map the directory dynamically via the shell anyway.
Exactly. The only information that should survive in your AGENTS.md file are hyper-specific, obscure tooling constraints.
We're talking about the exact shell commands required to execute a niche testing suite, or dependency anomalies that the model simply cannot deduce from standard Python conventions.
You are optimizing for minimum viable context. Every single additional token is a vector for the instruction tags. You want to provide just enough constraint to prevent a catastrophic environment failure, but not so much that you trigger hyper-exploratory paralysis and burn through your loop limit.
Right, and this rigorous evaluation leaves us with a highly provocative concept regarding the future of autonomous architectures.
Oh, this is the best part.
Yeah, the paper definitively proves that static, repository-level instructions impose a heavy reasoning tax on current frontier models. Looking forward, we have to ask a fundamental design question.
Might the entire paradigm of static agents.md files be rendered obsolete by dynamic context retrieval?
Exactly. It's a fascinating thought.
Instead of loading a fixed global set of rules into the context window at step 0, essentially polluting the prompt before the agent has even parsed the issue, ticket future agentic architectures might abandon global initialization entirely.
We could see frameworks relying exclusively on continuous, execution trace-based semantic search to synthesize localized working memory in real time.
The system would only retrieve the specific build instructions or style rules relevant to the exact file it is currently modifying.
Dynamically swapping constraints in and out of the context window as the state changes.
It would effectively eliminate the global instruction tax by replacing it with just-in-time localized retrieval.
And that might just be the key to unlocking the next massive leap in autonomous coding reliability.